I recently read a book on data visualization, and one of the recurring themes were these connecting lines. However, those were not straight lines, but these round, curved lines. So I was thinking, how would I pull it off in Houdini? And especially, how would I pull it off procedurally, so I wouldn't have to draw all these by hand? So here's my take on it. Let's start off with one single, simple curve, connecting a start to an endpoint. And what we want instead of this straight line here is this curved line. So how would you create those lines? Usually with a subdivision algorithm. That's about what you know from Illustrator. For example, when I highlight this line here and click on my anchor points, you can see they have these control vertices here, which drive the shape of this curve here. And what's happening inside Illustrator is these are not individual control vertices, but these are a full line connecting these two endpoints. So basically what's missing in Illustrator's display here is this line connecting those points here. So basically what we want to generate such a curved line here is a control spline that looks like this, just like this stepped curve connecting the start and the endpoint. So how do we construct such a line? Well, let's look at this in 2D first. What we do is we subtract the start position from the end position, resulting in a vector pointing from start to end in this direction. And note that, just to make it consistent with my code that I'll write later, I flipped the axis here, so y is pointing the direction, x is pointing upwards. Now that we have this d vector pointing from start to end, we can calculate the individual positions of those two intermediate points that we need to get this stepped line, with start being p0 and then p1 equals the position of start plus half of our d vector's x component and 0 of our d vector's y component. So this is not translated in y, but just in x. Likewise, p2, this point here, is the starting position plus 0.5 dx and 1 dy, moving it over here. So this results in a 4-point control curve. Again, just borrowing components from this d vector pointing from start to end, and then adding up those components to our start position and generating those two intermediate points. Now, in three-dimensional space, we need another third intermediate point, bridging the gap between start and end position in z direction too, resulting in these three intermediate points here. So first, we add to our starting position 0.5 times our dx component and 0 times our dy and dz component, then 0.5 times our dx component, 0 times our dy component, and 1 time our dz component, moving our point over here. And then finally, for the third point, to start we add 0.5 times dx and 1 times dy and 1 times dz, resulting in this curve having 5 points overall. So let's head over to Houdini and try that out. I'm going to start by dropping down a grid, dive in there, and scale it back to be 1 by 1. And having only 2 rows and columns like this, and also we want this oriented in the YZ plane. Next, let's scatter some points in there, and for our first trial, let's just use one single point here, and copy those 2 nodes, put them over here, and dial in our scatter with a different global seed, and move those grids off center, -1 and +1 in X. So we have this single point here, and this single point over there. Next, let's drop down a point triangle. And we will just assume that we have as many start as end points. In our case, only one start, one end point. And in this setup, to make sure start and end points have always the same number, let's just go into the first scatter, right-click on the first total count, copy the parameter over to our second scatter, and paste it there as relative reference. So I can only drive the total count with the first slider here. Okay, back into our point triangle. And let's first get our end position. Let's call this one end pos. And it's equal to our points position coming in through the second input slot. That's the input slot with the ID 1. So we'll just look up this point's position here. Also, let's create a second vector, call it pos. And it should be our current point position like this. Next, let's create our vector d. That's the one storing the difference from start to end. It's end pos minus pos, like this. Let's just check. Everything's still fine. And now let's get our intermediate points. So we already have the positions of our first and last point stored in pos and end pos. So we need those 3 intermediate points now. Let's create their positions. Let's call the first intermediate point P2. It's the second point. And it should be equal to pos, our starting position, plus 0.5 times dx and 0 on dy and dz. So let's create a vector using set 0.5 times d dot x and 0 times dy, that's 0, and 0 times dz, that's 0, 2. Let's create our second intermediate point. Position should be equal to position plus 0.5 times dx, 0 on the y-axis, and dz on the z-axis. So 0.5 times dx, 0 on y, and 1 times dz, that's dz, like this. Let's create the third intermediate point position. Pos plus a vector that will create, this time again, 0.5 times dx, 1 times dy, and 1 times dz. So 0.5 times dx, 1 times dy, and 1 times dz, like this. So now we only created those points positions. Now let's add the actual points into our geometry stream by creating an integer, storing the new respective point number. Using the add point function, adding to our 0 geometry stream a point at the position P2, and let's copy this line here and paste it 2 times, creating a third and fourth point at their respective positions. So we now have those additional points created in here, and also we need to copy over this point, the endpoint, into our geostream. So let's finally create that too. Again, pasting this line one more time. NPT5 is the endpoint, and the end position is npos, like this. So we have all those points. Now all we have to do is connect them using a polyline by creating a new prim, using the add prim function. And to our geostream, we add a polyline using our current point number as a starting point, then those intermediate points. And if I'd want to add the fifth point here, NPT5, the endpoint, that would yield an error, because add prim can apparently only take in 4 arguments for the points that it will directly put into a polyline. So let's instead use the add vertex function to add the last point to our polyline, adding to our new prim NPT5, our last point. And now we have this line going from start through those intermediate points to the end. Alright, so now we have this control line, you say, but there is no rounded curve. How do we do that? Well, by just dropping down the resample node, wiring in our control spline here, and then setting our resample node, maybe dial back the length to 0.02, and then instead of treating the polygon as a straight edge, let's treat it as a subdivision curve, and highlight it, of course, and you can see we now have these neat interpolated curves. Let's overlay the control spline here, and you can see we're getting these round, nice shapes. That should also work if we increase our start and end points, so let's try doing that. And we can see, yes, that works. All those connect through this intermediate plane, which now sits right in the middle between start and end point, and form those curvy lines. So how can we control the appearance of those individual subdivision curves? Well, let's add some parameters to our control splines to do that. First, I maybe want to be able to offset this plane where all of these intermediate control points will be created. So now I'm just using this factor of 0.5. So let's instead use a variable to do that. Maybe create it up here, a float called O for offset. Then let's use a float slider, which we call offset, to dial this in. Create our interface element here, just drag this down a bit so we can see it. And instead of 0.5, let's just use O directly down here. And now we have this control slider where we can dial in this plane. However, this still moves all those control points for each individual spline in uniform. So to give this a bit of randomness, let's create another float, call it rand O for rand offset. And let's use the random function, initialize it with our ptnum, and maybe a seed, which we'll be later able to dial in. And let's fit that using the fit01 function, because the random number generator always outputs a value between 0 and 1. So let's fit that between -O and O, and multiply this with an amplitude slider so we can dial in the effect of that. Let's create all those sliders. For this to be effective, there's not much happening now. For this to be effective, we need to add this to our O. So O plus equals rando. And now, for each individual line, we are offsetting our intermediate point plane by a bit. And we can dial this in using the seed value here and the offset amplitude here. Finally, sometimes these bends can look a bit strong here when we're looking at them from a certain angle. For example, in this corner here, that's really a strong bend. And to counteract that, what I can do is move those individual points closer to their respective start and end points using another float value, which we'll call maybe S for softness. Let's create that. And what I want to do is I want to drive the X offset on my first and last intermediate point and the Z offset on my medium intermediate point. So what I want to do in the first point, I want to have S drive how closely this point is to our original start position. So I want to take our original O and subtract from it S times O. Likewise, let's just copy this. In my last intermediate point, I want to add this to our multiplier here. So when I dial in the curve softness now, you can see this is what happens. We're moving those first and last intermediate points closer to their respective start and end point. And also I want to have a similar effect for the middle intermediate point by multiplying the DZ offset times 1 minus S. So now I have this curve offset slider, which I can use to dial in the softness. However, what you can see here, this allows to overshoot some of the values. So back here, those values of my control curve protrude past our endpoints here and yield those weird archy results. I mean, if you like them, you can leave them. If they're not for you, what you could do here is use a clamp function to clamp this value that we calculate in here and here to a value between 0 and 1. For example, like this, clamping this value to be between 0 and 1. And doing the same down here. Like so. So now we cannot overshoot those points here. Well, and that is how you build procedural control splines for subdivision curves. As always, I'm intrigued to see what you guys use this for, if there's any data viz project you have, or maybe scientific visualization, or a fun UI for a sci-fi movie. We're always intrigued to see what you guys cook up. And if you want to know more about Houdini, get access to exclusive in-depth courses, you might want to visit our Patreon. And if you already do support us on Patreon, thanks so much, and a very, very special thank you goes out to Important Looking Pirates, Kyoko Sakane, Joseph Howerton, Nick, Chris Hebert, Refik Anadol, and Mohammed Al-Abri. Thanks so much, guys. And until next time, it's cheers and goodbye.